going to look at the alkali metals in this video. The alkali metals is a group of the periodic table. A copy of the periodic table here. And the alkali metals are on the left-hand side. So the alkali metals are lithium, sodium, potassium, rubidium, cesium, francium. Now I will refer in this video to moving down the group or going down the group. What I mean is going from lithium to sodium to potassium, going down the group that way. It's worth knowing. So, in what group of the periodic table of the alkali metals? Well, periodic table group is group 1. First three members of the group are lithium, sodium, and potassium. Okay, you don't need to learn the symbols or the names. You'll be given a periodic table in the exam, but it helps if you know. Are the alkali metals soft or hard? They're very soft. Alkali metals are famous for being soft. They can be cut with a knife. Okay, so your teacher has probably demonstrated this too. And they will have cut a piece of lithium off with a scalpel, and probably quite a blunt scalpel if it's anything like the ones I normally get my hands on. They can be cut with a knife. Okay, so they're not stereotypical metals that are strong and hard. They're soft and quite malleable. Do they have high or low melting points? They have low melting points. Your teacher probably put a bit of sodium in the water to react it and watch it so you could see it react. Sodium will melt into a ball when it reacts with water. So as I said, you probably saw the sodium react, and about a second after it starts reacting, you see it change shape and become very spherical. And the reason it does that is because the heat given off from the reaction has melted the solid, and it's become a liquid. It becomes a ball of liquid when it reacts with water. So the melting point must be very low for that to happen. Right, you're often asked to describe the reactions of the alkali metals with water. And there's three very similar reactions for every single one of them. Number one, they move around the surface of the water because they have low densities. You wouldn't expect a metal to move around the surface of water, would you? You'd expect it to sink because metal's normally dense. Well, these have low densities, move around the surface of the water. Okay, it gives off a gas. It gives off a gas. You can say that in a number of ways. You can say it fizzes, or it gives off gas, or it bubbles, or it effervesces. There's still only one observation. Okay, the third observation. The product of the reaction dissolves in the water. The metal doesn't dissolve, the metal reacts and the product dissolves in the water. What is the pH of the resulting solution? Well, after that product is dissolved in the water, the pH becomes 13 to 14. That makes it a strong alkali. What ion does an alkali produce in water? Well, that's year 10 revision. It's the hydroxide ion. Okay, the hydrogen ion is what makes things acidic, and the hydroxide ion is what makes things alkalis. Does sodium react faster or slower? So it reacts faster. So it's much the same as the reaction of lithium, but it is faster. It's more reactive. Okay, next one down the group is potassium. Describe what you see when potassium reacts with water. Well, the same as the last time, really. It moves around the surface of the water. Okay. It doesn't bubble this time or give off a gas. Well, it does give off a gas, but you don't see that. Moves around the surface of the water. Let's finish that one first. So we're not going to say bubbles or fizzes or effervesces or gives off a gas. We're going to say the potassium burns. The reason the potassium burns is because it's giving off the gas so quickly, and the potassium is getting so hot, the reaction is so exothermic that gas catches fire. The potassium burns. And it burns with a very characteristic flame. It burns with a lilac flame. Now, only potassium burns with a lilac flame. Needs remembering. And the last one, the product of the reaction dissolves in water. So there are observations for potassium. You get asked about observations for these a lot. As you go down the group, they get ever more reactive and the reaction gets ever more extreme. If you're asked for rubidium, you'd say it moves around the surface of the water and it reacts explosively, and the product dissolves at the end. So lithium with water, word and symbol equation. I'm just going to do symbol equations because I'm running a bit short on time in the video. So lithium plus water, let's put some state symbols in, solid, gas, liquid for water, what am I talking about? liquid for water. It reacts to make lithium hydroxide. The formula of all the hydroxides, the hydroxide ion is a single negative charge. So the formula of all the alkali metal hydroxides is always one of the alkali metal and one of the hydroxide ions, because the lithium is in group 1 of the periodic table. It has 1 electron in its outer shell, so when it reacts it loses that to form 1 positive charge. So there's our hydroxide plus hydrogen, and that is going to be aqueous because that dissolves in the water, and that's going to be a gas. Balancing out 2, 2, 2, and that one there 1. Now all these are the same now. So sodium is going to be 2Na plus 2H2O makes 2NaOH. Let's just write it in quickly. Plus H2. Okay, you can do the potassium on your own. Okay. All right. Test for hydrogen. We absolutely have to know that. Lit splint. Add a lit splint to the hydrogen and squeaky pop. If you get a squeaky pop, you know the gas is hydrogen. So you can collect the gas, the hydrogen gas from this reaction, put a lit splint next to it. If you get a squeaky pop, it proves it's hydrogen. What's the pattern, the reactivity of the alkali metals groups? As you go down the group, okay, this is vital. Reactivity increases. Okay, back to the periodic table. Let's just look at that again. So that's so important. As we go down this group, from lithium to sodium to potassium to rubidium to cesium to francium, the reactivity increases. You put cesium in water, it explodes the bowl. A very famous video about that. Okay, so lithium fizzes a bit faster, burns, explodes, the whole bowl goes up then. Okay, right. How would we expect rubidium to react with water explosively? We've said that. Draw the electronic configuration. So what we're going to do now is explain why they get more reactive. So I'll spend a bit longer on this. To understand that, we have to draw the electronic configurations of each of these. Now I've got the atomic numbers of each of them here. So dot for the nucleus for lithium, 2 electrons on the first shell and 1 on the second shell. So it's 2, 1. Okay, dot for the nucleus on the sodium, 11 electrons and 11 protons on the nucleus, so 11 electrons in total. 2 electrons on the first shell, 8 on the second. Okay, and 1 on the third. So hopefully you're seeing they've all got 1 electron on their outer shell. They're all in group 1 of the periodic table. Potassium, 19 protons on the nucleus, so 19 electrons in total on the outer on the shells. 2 on the first, 8 on the second, 8 on the third. So hopefully you're seeing as we go down the group these atoms are getting bigger, and 1 on the fourth shell. There we go. So it was 2, 8, 1 there, and 2, 8, 8, 1 there. Okay. This is essential. We can see this if we're going to understand why they get more reactive as they go down the group. Okay. So let's try and keep that in shot as we're answering this next question. All right. Use the diagrams. Let's just see if I can reposition that a little bit better. There we go. That's possibly better. Use the diagrams showing the electronic configuration, these, to explain why potassium, that, is more reactive than lithium, that. Okay, so the first thing you have to know, the first thing you have to appreciate, okay, atoms, or elements, are more reactive if it is easy for them to get a full outer shell of electrons, to get a full outer shell of electrons. This is why these are all reactive metals, because to get a full outer electrons, all they have to do is they all have to lose just 1 electron. Lithium has to lose 1 electron, that's quite easy, so that makes it quite reactive. Sodium has to lose 1 electron, that's quite easy, so that makes it quite reactive. Potassium has to lose 1 electron, that's quite easy, so that makes it quite reactive. If they had 2 or 3 electrons on their outer shell, that's less easy because they have to lose 2 or 3, makes them less reactive. So how easy it is to get a full outer shell links to the reactivity. Now, next thing we have to say, okay, the nucleus is positive. The nucleus is positive. The nucleus is positive because all the protons live in the nucleus and protons are positively charged. Okay, so the dot here is positive. Positive. Dot there is positive. The nucleus is positive. Next thing to say, the outer electron is negative. Okay, the outer electron there is negative. The outer electron there is negative. Can we see that? Okay, so potassium is more reactive than lithium. Potassium, therefore, finds it easier to lose this outer electron than lithium does. Let's write that. Okay, potassium loses its outer electron more easily. Okay, and there's two reasons for that. There's two reasons. The easiest one to understand, I think, is distance. Look at the distance between that positive nucleus there and that outer electron there. It's quite large. Look at the distance there between that positive nucleus there and that negative outer electron negative there. Okay, it's quite small. Now, opposite charges attract. Okay, opposite charges attract. So the attraction here is going to be greater because the distance is less. The attraction here is going to be less because the distance is more. Okay. Potassium's outer electron is further away from the nucleus, so it is more easily lost. Okay, because the nucleus is positive and the outer electron is negative. Okay, let's just put a little bracket in there. These attract. Okay, but the further away, the weaker that attraction is. And so that makes it more easily lost. That makes it more reactive. There is another answer, which is absolutely fine, and it's possibly even better. It's just a bit more hard to understand, but I mean, this answer here for GCSE is fine. You might hear people saying, because they are correct, that potassium loses this outer electron more easily because it's further away, and because there is more shielding from inner shells. There's only one inner shell here, but here there's 1, 2, 3 inner shells, more shielding. That also weakens the attractive force. Okay, so what we've said here is potassium's outer electron is further away from the nucleus, so it's more easily lost. Also, there is greater shielding from inner shells. You don't have to include that last bit if you want, but it makes a good answer into a great answer. It just won't get you any more marks at GCSE. Okay, and that's a whistle-stop tour through everything you need to know for GCSE for the alkali metals.